I can't let Nathan Nelson down. My story.
I'm like, did Nathan Hell yeah. I'll have him out.
I'm pretty sure isn't it a series parallel? Because you saw it.
Okay, so,
Yeah.
Yeah, I
the
can
last of the three, the first of the three last units is on circuit. So, there's, and we're going to use this program that's allowed, it's a certain effect simulation, it's called Circuit Builder. And it's nice because of the fact that you can add things in, you can change the resistance, you can measure things, and it's a completely idealized situation where there's no internal resistance on the wires. In reality, that isn't true. You automatically know if the circuit is working because things automatically light up where they don't. So you can automatically see what's going on. And in contrast to that, when we go to the back of the room and you actually, like yesterday, when you actually look at circuits and you try to build them, it's not nearly this nice. And it's much more frustrating. So like even during lunch, I was trying to get that circuit to work back there. Oh my God, I just wanted to scream because of the fact that I had put one LED light in the wrong sequence and it shut down the entire circuit. And then it's like, is it a broken connection? Is it the LED light being wrong? Is the capacitor in the wrong direction? Okay, so let's talk about some things. So let's start with the idea that when you have a circuit, and I've got to switch down here. So if you're going to have a circuit, you can kind of think of this is, and it's a good book in terms of describing electrons. And ironically, the name of the book is There Are No Electrons. It would sound like an odd book about electricity, but it is. And so it describes electrons as being, in the book it talks about them being greenies. I don't know how they picked up the name. I'm not sure, but that's what it's called. So, if you look at electrons moving, and the fact that they are going to like leave the battery with a certain amount of energy, and that energy is going to get dissipated. Maybe it goes through a resistor, maybe it goes through a light bulb, maybe it goes through a capacitor, okay? So the sole function of the battery is to give energy to the greenies. Now, here's the story. If the greenies are going to move, the greenies have to have a complete highway to drive around it. So as soon as I break that circuit and I open up that switch, the greenies go, oh, I have nowhere to go. Now, there's a couple of things that are wrong with this. And let's just get this out in the open. Let's just get this out. So if I close this, when you look at the battery up here, the top of that battery is the positive terminal. And the easiest way to remember the positive terminal is that it's going to have like a little knob that sticks out, and that kind of looks like a plus sign. So that's the easiest way to remember, oh, that's the positive end of the battery. So this is up here. What I'm using is what the conventional motion of electricity and how it moves. So this harkens back to Ben Franklin. This is all Ben Franklin's fault, okay? So when Ben Franklin studied electricity, he had a 50-50 shot. He said, is it going to be the positive charges that are going to move, or is it going to be the negative charges that move? He was an optimistic guy. He said, I think it's the positive charges that are going to move. And that's how electricity started. They said positive charges. Now, this is in the 1700s. We had no knowledge of electrons, protons, electric fields, anything like that. So until we figured that out, everybody just stuck with that convention. So that convention was around for about 120 years. That's a long time to get ingrained into the psyche and the thought process of science. And so later on, when we figured out that it was actually electrons, the die had already been cast. And Ben Franklin was a nice guy. It's like, man, we can't go back on Ben. So when you talk about the conventional movement of electricity in a circuit, how it's defined in the conventional manner is it's positive charges moving from the positive terminal of the battery going around the circuit, in this situation, clockwise. Okay, that's the conventional way. Now, what we figured out later on, and once we do magnetic fields, you'll see how we came to this conclusion. But we can't really prove it until we get to magnetic fields. What we've actually eventually figured out is that it's electrons. So if you go with, and switch this over to the electron movement, notice the electron movement is in the opposite direction, okay? So unless I specifically tell you to talk about the movement of the electrons, when you describe a current, you're talking about the movement of the positive charges, okay? This is actually even not right, okay? And you're going, well, we have a bunch of things that are wrong. It's the nature of science. So we talk about the movement of electrons. And the movement of electrons are important, don't get me wrong. If you don't make electrons move, you don't have a circuit, okay? The electrons have to be able to move. But in case you haven't figured out, the speed of electricity is pretty fast, all right? But what you can get into is what's known as electron drift, okay? Electron drift velocity. Electrons themselves actually move relatively slowly, like through a copper wire, okay? They actually don't move that fast. What is propagated at the speed of light is the electric field that's created by the movement of the electrons. So a lot of people have this analogy, and it's not bad, that you can have, imagine that you have a garden hose hooked up to the house, and you have a spray nozzle on the other end, okay? Well, that tube is full of water. Soon as you open up the nozzle and you hit spray, oh, the water comes flowing out. Electrons are somewhat like that in terms of like a circuit. So obviously, I shut out the lights here. Oh, I in effect shut the valve on the hose. So when I throw that switch and turn it back on, then it's like opening up the spray nozzle on the end of the hose. Oh, now the electrons can travel through and complete the circuit. When you plug your phone in at night to charge your capacitors and recharge your batteries, basically what you're doing is that you're taking those electrons, and in that battery, you're giving that battery the capacity to take the electrons and give them energy so that as they circulate through your phone throughout the day, as you watch TikTok videos or Snapchat or whatever time you waste on your phone, you're taking energy from the battery because it takes energy. Because, oh, you're going to look at your little screen and you're going to see images of a cat video, okay? Well, to produce the photons that allows you to watch the cat video, Shaden, and so that's going to take energy. So by virtue of that fact, oh, that energy's got to come from somewhere. And obviously, you all know this, if you let your phone go too long, your phone goes dead. Because your battery has lost the capacity to recharge the electrons as they go through the circuit. Okay. Now, a little bit about terminology. And we're going to spend a lot more time. This is just kind of a very introductory set into this. So, to have a complete circuit, the wires all have to be connected. And typically, we're going to have a single battery. We're going to go off batteries as the power source. Grids and an alternating current is a whole ball game of pain and suffering. We're just going to work with simple, what we call DC or direct current circuits. We're not going to get into AC circuits because that gets weird really, really fast. Okay, so we're just going to work with DC currents. So, and this is what we talked about yesterday. So these two bulbs are in parallel. So what's happening, do you want to leave it like this, or do you want to go to the conventional current?
Conventional.
Okay, all right. Some people, all right, we'll go with conventional.
Give me arrows.
Okay. So, you can think of this as if you like the water analogy. So this is like a stream of water. And it hits that point up there, and it has to make a decision. Am I going to go right? Am I going to go left? Now, in this situation, see that 10, and it has the capital Greek letter ohm on the end of that, okay, omega. So that's a 10 ohm resistor. Resistors is literally, as the name implies, how much resistance there is within that system, whether it's a resistor, whether it's a light bulb, whether it's a switch, whatever that is. The higher the resistance is, the more energy it takes to get through it. So both of these are 10 ohm light bulbs. So those two bulbs up there are in parallel. So it hits, it's like a river, it splits, those two are in parallel. This one is in series. So here's how you can tell the difference. So you've got two bulbs that are in series, or in parallel up there, and then if it's part of the circuit itself, that's going to be in series. So here's one thing that you can do. If I come in here and I break this switch, okay? Notice that that top bulb goes out. But what happens to the bottom bulb? Well, it stays on. Here's the point of the story. It stays on, okay? So knowing that, let's just start with a simple analogy. Is your house wired in parallel or in series? Parallel, because if your house was wired in series,
One failure and you have problems.
well, if you have one bulb that goes out in your house, guess what? Everything goes out, okay? So your house is not wired in series. Now, if you've ever bought Christmas tree lights, okay, and like the strand doesn't work, especially the older style of Christmas tree lights were wired in series. So if you had one bulb go out, the whole strand went out. And then you're trying to find that one bulb that had gone out, and it's like, the newer ones are wired in parallel, so if you lose a bulb, you don't lose all of it. Now, here's the difference. So I'm gonna connect that back up, okay? But now, if I break this one,
Whoa, there goes the whole set.
hold on. So if I break that one that's in series, I lose the whole thing, okay? So that's a simple way to tell, hey, is it wired in series or is it wired in parallel? So let me connect this back up. So one of the key things about circuits is terminology. So amps, which is measured by the letter I, and I'll write all this down. Amps is a measure of how much current flows per unit of time, and it's represented by the capital letter I. So there's different ways that you can measure amps. Now, this is kind of cool because of the fact that this is what we call a contactless amp meter. And these actually exist, okay? You just hold it over the wire and you get a reading, okay? And it measures your current. So this is 0.6 amps, which means that you have 0.6 coulombs per second. So current is charge per unit of time. It's coulombs per second. So this is 0.6 amps. Now, there's a deal we'll talk about. This is called Kirchhoff's rule. Kirchhoff's rule says that the sum of the current at any point has to equal the same value. Instead of like being the law of conservation of mass, it's like the law of conservation of current. So I've got 0.6 amps flowing into this. So if I move this over here, notice that that's 0.3, and the other one is 0.3. So those two, 0.3 and 0.3, add up to the original current that was going in there. That was simple. I got a 10 ohm bulb, Mother Nature goes, cool. Now, an interesting thing happens. If I take this bulb And let's say that I increase that resistance to 42, okay? So, the current has dropped to 0.5. Later on, you'll see why that works, okay? But the current has dropped to 0.5. But now, if I move that up here, that 42 ohm is 0.1. The lower one is going to be 0.4. So notice that they still add up to the 0.5. This is what's known as Kirchhoff's rule. So it's just like current has to be conserved. Now, this is where don't ask how it knows. Just accept it. Notice that that top bulb has a much higher resistance. Lower bulb has a much lower resistance. So when that electric field gets to this junction right here, it has to make a choice. Do I go to the top? Do I go to the 42 ohm? Or do I drop and go down through the 10 ohm? Mother Nature, like most people, is a little bit lazy. So Mother Nature goes, it's going to be much easier to go through the 10 ohm than it is to go through the 42 ohm because the 10 ohm has much less resistance. So now, how do the electrons know? Doesn't matter. Okay?
You just take the
It,
positive resistance.
it works. Okay? It just works. They don't know, they don't have a consciousness for the most part. So that's what you got going. So, but notice that here's what I want you to get out of this, is that they both are going to add up to what you have at the beginning. Got that? Now, this is this nice, clean, elemental thing. You're going to be using this program a lot. And it's weird. Some people, like when I built this, I kind of try to build it relatively nicely. And you can move it around, and you can get like right angles and things like that. Some people just go, oh, whatever, right? You know, it looks like,
Bro, you're about to see.
yeah, you can have that, you can
That
have
makes me
No, pull that inside the other one so it wraps through. Come on.
that.
You're so good at
Okay.
Okay.
So, yeah, I think you just did, okay.
Perfect.
Oh, yeah.
Let's get you there.
Okay.
Oh, boy.
So, how you do your circuits is completely up to you, I don't care. So this is what this looks like really nicely. Now, come back here.
It's just less. I don't want to.